So today, the topic, we're just going to call this slopes of parallel lines. So slopes, not parallel, parallel and perpendicular. You see both of those on here. Slopes of parallel. This is going to be an exercise in writing small for the topic. Parallel and perpendicular lines. And today is the very last day of January. All right, so slopes of parallel and perpendicular lines, that's our main topic today. And you can see there's an example, like a little visual example of what parallel lines look like off to the side here underneath where it says parallel lines. Can anybody give me just a quick definition of parallel lines? What do we know about parallel lines? In terms of what they look like here, how would we define that? Or how have you heard that defined before? Ash? Yeah, they kind of run along next to each other the whole way, right? I think the way that we're going to write this down, and this definitely reflects that, I think just the most straightforward way to write this, though, is that if two lines are running along each other forever, that means that they will never intersect, right? Like there's no way that they're ever going to start like going towards each other and crossing. So we're going to say that definition of parallel lines are lines that never intersect. Good morning. These two right here. So parallel lines are lines that never intersect. Now, here's where we're going to do a little bit of an activity. I'm going to show you some things. I'm going to show you some lines on the board, and I'm going to be kind of like manipulating them with the mouse. And I want you to pay attention to, again, the title of this is called Slopes of Parallel and Perpendicular Lines. So that's going to be the main thing to pay attention to for this first one that we're going to take a look at. So let me get this up here. All right. Switch. Share here. Great. Okay. So I want you to look at something as we're going through this, and it's up here. The first one right here. We can see that we have a slope up here of 0.6. Can everybody see that? And I know we don't use decimals for our slopes, but this is not really what this is about right now. So you can kind of ignore the fact that the slope is shown as a decimal right now. What I want you to pay attention to is the slope of this top line here, M. And if I scroll down here, so we can see the other one, there's the other slope down here, and I'll make that one a fraction because this is how we generally see fractions. So the slope of the red line, I know it's going to be tough to see, but the M way up there, that 0.6, that's the slope of the red line on the bottom. The slope of the green line on the top is the value of M down below where it says 3/5. And actually, I'm going to change that back to a decimal just because it'll make it easier to see what's going on. 0.6, okay? What do you notice about the slopes right now of the red line and the green line? You can tell me. What's that? They're both 0.6, okay, right? They're the same slope right now. And the lines, the red and the green lines definitely appear to be parallel. So watch what happens if I change the slope of the red line. And let's say I move it back to right there. All right, so now the slope of the red line is -1 up there. Look at the slope of the green line. What is it right now? And what's the slope of the green line currently? That's this one down here. -1. And the slope of the red line up here? -1. Whereas they were both 0.6 before. Let's try something else. Let's say I'm going to want to increase this to, let's say make it 2 for the red line. So the slope of the red line is now 2. What's the slope of the green line? Down at the bottom there. 2. So what do you think we could say about the slopes of lines that are parallel? Based on what we just saw here. We have 0.6, 0.6, -1, -1, 2, 2. Okay, and the slope of each line was always what? If these lines were always parallel, what did we notice about the slope of both lines? They were always what? Okay. But when I stopped changing them, what did you notice about, like right now, the slope of the red line and the slope of the green line they're the same, aren't they? And they were the same when it was 0.6. They're the same when it was -1. If I change this again to 2.8, red one up here, slope 2.8 down here, green one 2.8. So if lines are parallel, then their slopes are the same, which makes things pretty convenient actually for us because we know how to find the slope of a line. And so if we can find the slope of one line, we can find the slope of another line. If the slopes are equal, then we will be able to say for sure that those two lines are parallel. So that's the first one we're taking a look at here. So let's go ahead and put some information in about parallel lines. So algebraically, how do we know if two lines are parallel? What do we know about the slopes of them? What did we just say? The slopes are what? The same. Yeah, they have the same slope. So they have the same slope. And just a reminder that slope is m. So they got the same slope. A quick little example over here would be, let's say y equals 2x plus 1 and y equals 2x minus 7. So the slopes of those two lines right here are 2. The y-intercepts are different. This one's 1, that one's -7. So it's not the same line, but because they have the same slope, that means that they are parallel. Now for today, that's kind of the easy one. Between the two of these, parallel and perpendicular. The fact that the slopes are the same on parallel lines, that's going to be, I think, the easier one to kind of see and understand, because identifying a number that's the same, not a really difficult thing to do. You can point to it and be like, all right, that's the same. The other one that we're going to look at, though, has to do with perpendicular lines. So I've got another graph up here that I'm going to be changing, and I want you to take a look at what happens here. So this one's a little bit different, and I think this one's a little more interesting. First of all, these two lines are perpendicular, and we'll get to a definition. Good morning. We'll get to a definition of perpendicular lines real soon here. But first, we're going to take a look at the graphs. So these two lines are perpendicular. And just so you know, perpendicular lines, they intersect to make a right angle. We'll get that definition written down in a moment. A right angle just means it makes like a 90-degree, like a T, right? That's perpendicular. So when lines are perpendicular, they intersect at a right angle. They intersect at 90 degrees. So they form like a perfect T. Now, in terms of the slopes, because that's what we're dealing with today, I want you to pay attention again to the slopes of these lines. So the slope of the red line, I'm going to point these out to you so you can watch what happens when I change these. The slope of the red line is right here. This is the m equals -2. That's this red line right here. The slope of the purple line is the one right underneath it. It's this one right here that says 1/2. So I want you to watch this number here, and I want you to watch this number here, and I want you to see if you can notice a relationship between those two numbers. This one's going to be, like I said, this one will be a little bit more challenging, but I want you to really pay attention to what's happening with those numbers as I move this slider right here. So if I change it to -1, so now the red line has a slope of -1, and the purple line has a slope of +1. If I move it a little bit further and I say, let's say my red line has now a slope of 3, my purple line now has a slope of -1/3. I'm just going to go one by one now and see if you can notice a difference, see if you can see a pattern here. Slope of 4 for the red line, slope of -1/4 down here for the purple line. Next one, slope of 5 for the red line, and a slope of -1/5 for the purple line. Do you see a pattern? Ash? Uh-huh. Yeah. Okay, so it seems similar because the 5 in the red and the 5 in the purple match, but one of them is a fraction with a 1 above it, and one of them is a whole number. I agree with that. What else do you notice that's different between the two? So that's one of them. If I go up one more, I've got 6 for the red one, which again, we would write as 6/1, right? If we were graphing this, the red one has a slope of 6/1, the purple one has a slope of -1/6. So far we can see that they're kind of flipped over versions. What else is different about those two numbers though? Apart from the fact that we call these reciprocals, right? One of them is flipped over, they're flipped over versions. What else is different between them? There's something in those numbers that's a little different. Yeah, one of them is a negative. Now watch what happens if I make the red one a negative. So now, right now, the red one is a +6. What if I were to go back and I made this a -6? So the red one now has a slope of -6 or -6/1. And the purple one is now a +1/6. So number-wise, what could we say? I know this one's a little bit harder to describe. The last one was the slopes are the same, right? That's a pretty easy thing to describe. How could we describe these? So Ash was saying one of them was a whole number. One of them was like a fraction version of that whole number, right? With a 1 over it. And then you also said we had a positive and a negative. Yeah, and that stayed true. Yeah, actually, that's a great way of saying opposite and a fraction. And we're actually going to use the word opposite, and we're going to use a specific word about those fractions as well when we write our definition. But I want everybody to notice that, that whenever we were dealing with these two here, those two types of lines, when we have perpendicular lines, one was a positive number, one was a negative number. Again, watch this. The red one is negative, the purple one is positive. The red one's negative, purple one's positive. And as soon as I go positive, the red one is positive, now the purple one's negative. And there's a fraction version of that whole number because it got like flipped over, right? So that is what we're dealing with perpendicular lines. We'll write a little bit more precise definition about the comparison of that here in just a second. So here we go. Our definition of perpendicular lines, first of all, are lines that intersect at 90-degree angles. So that's that whole 90-degree right angle forms a nice exact T letter when they intersect. So that's how we can define perpendicular lines. Now, number-wise, algebraically, in terms of what we saw with the actual numbers for the slopes, we can say this. They have, I'm going to use the word that Ash used, opposite. And here's the fraction word that I was talking about. They have opposite reciprocal. That would be flipped fraction. They have opposite reciprocal slopes. Reciprocal, remember, is just a flipped fraction. So we'll do a quick example, and then we're going to run through different ways of determining if two lines are parallel or perpendicular, perhaps neither, depending on the slopes of two lines. So number-wise, parallel lines have the same slope. Number-wise, perpendicular lines have opposite reciprocal slopes. For example, if I have y equals 2x plus 1 as my first line, the next line that is perpendicular to it, First of all, the y-intercept here, the +1, doesn't matter at all. The y-intercept has nothing to do. I just want to make that clear. Parallel lines, perpendicular lines, the y-intercept has nothing to do with whether lines are parallel or perpendicular. It's all about the slope. So y equals 2x plus 1. And then the other one could be y equals -1/2 x. And then we can just say any number we want here. We'll say +5. It's all about the slopes. And I really want to highlight that. So I am going to opposite reciprocal. I'm going to circle the 2 and the -1/2. So that red right there, I'm highlighting opposite reciprocal slopes. In fact, I'm going to make this 2/1. I think that makes it easier to see that it's a reciprocal when you have that denominator. That's another reason why way back, a few weeks ago, when we first started talking about slope, I recommended it's always good to write these as a fraction. This is another reason why it's good to write slopes as a fraction, even if it's a whole number, because it's a lot easier to see when you flip over a whole number. It just turns into a fraction with a numerator of 1. So we have a positive 2/1 and a negative 1/2. This is true of every single perpendicular line. One slope is positive, one slope is negative, and they are flipped over versions of the exact same fraction. So, for example, we are going to run through some negative reciprocal or opposite reciprocal. By the way, this right here, negative reciprocal, is the same thing as opposite reciprocal. Let's see, opposite. So if you see negative reciprocal, it means the same thing as opposite reciprocal. I prefer the word opposite because if a number starts negative and you say negative reciprocal, you're like, well, it's already negative, so I don't need to change it. Well, it's opposite, so we need to change negative to positive. So I prefer opposite. You will also see the word negative reciprocal. Yes. Yeah. Yeah, that's good. Yeah. Yep, opposite sign plus minus. Yep, exactly. That also, it makes perfect sense. So first of all, this is a fraction. So examples of opposite sign reciprocals or negative reciprocals, it is a fraction flipped, and I'm putting flipped in quotations because that's not the technical term. Reciprocal is the actual word. And the signs, here we go, here's the word sign. So, and the signs are switched. So there's that word sign again, like Miss Eddie was just saying. So opposite signs, we switch the signs, one's positive, one's negative, and we flip the fractions. Both have to happen at the same time. All right, let's have a look at just some basic examples of determining opposite reciprocals. Then we'll get into some math. So here we go. Number one, the opposite reciprocal of positive 3/4. First of all, this first one is positive, so the next one must be negative. So that would be negative, and then we flip the fraction over, so it would be 4/3. So positive 3/4 and negative 4/3. One's positive, one's negative, and they are flipped over versions of the same fraction. Next one here, number two, we've already seen this one, 2/1. So somebody tell me, what's the answer to the opposite reciprocal of this number here? We've already used this as an example. Negative 1/2, good. So positive 2/1 means the next one has to be negative, and flip over the fraction, negative 1/2 or negative 1/2. All right, number three. This time we're starting it with a negative number. So this one's negative, so the next one has to be what? If the one we're starting with is negative, the next one has to be what? I know we're tired, but I know we're also listening. So what is it going to be? -2, positive, good. And then flip over this fraction. What does that turn into? 8/7. There you go. Positive 8/7. Nice. So -7/8 to positive 8/7. One's positive, one's negative, and they are flipped over. Number 4, we got 1, which is the same as 1/1. So if we make this negative and we flip it over, it's still just 1/1. So positive 1/1, negative 1/1. But they're still flipped over versions of the same fraction, even though it's the same number all the time. One's positive, one's negative. Now this last one, I know that I've mentioned this before. We didn't write it down though. So I'm wondering if anybody remembers, what would be a perpendicular slope to 0? Or what would be, I'm going to use a pencil for this initially because I'm not going to stick with my answer. But I know that we've mentioned this before. I know I've talked about it. So 0 would be, if we wanted to, we could make it 0/1, right? Because anything over 1 makes the whole number a fraction. So 0/1, which means technically speaking, if we were following this exact same pattern, we would write -1/0, right? That's what we should be writing. And I'm writing this in pencil because I'm not going to keep this. So you don't need to write this down. But the issue that we run into is that even though like number wise, this makes perfect sense pattern with what we've been doing, but 0 divided by 1, that's this number on the left, or let me do the fraction, 0/1 is 0. So that's fine, right? That's what we started with, 0/1. Now, if I flip this over and I make it negative, we can do negative and then 1/0. What do you think is going to happen? Anybody? What's that? Okay. Any other guesses? So we say it's going to be another 0. Any other guesses? Oh, wait a minute. We've seen this before. What do we write when we see this? No, we're not going to write 0. And the reason why, that's a great, like, I mean, honestly, logically, yeah, it seems like we would. But the first one that we typed in actually gave us an answer equal to 0. And so actually, this is a little bit easier to see here. 0/1 was 0. -1/0 was error. So it didn't give us the same answer. Let me ask you this question. What kind of a line has a slope of 0? Oh, Elena? Undefined, yes. 0 and undefined. The reason is because, where it gets a little weird at the end here, 0 and undefined, those are opposite reciprocal numbers. -1/0 gave us an error, and an error means it can't do it, which means it's undefined. Think back, a week and a half ago where we did those horizontal and vertical lines. Horizontal lines always have a slope of 0, which would be this first one. Perpendicular to horizontal would be vertical. A vertical line, as we've learned before, has an undefined slope. So these two here, going to be a little tricky to remember. This is one of the main reasons, by the way, that it's really important to take notes. For those weird like side kind of like cases that don't fit with everything else that we do. The big idea is it's absolutely important to take notes, but when you get those kind of like special cases here and there, it's even more important to have your notes on that. That way you can look back, because those are the things that we don't see very often, which means that they're going to be a little bit harder to remember. And if you have it written down and you can go back to it, you'll remember it a lot better that way. All right. So that's where we're at now. We're going to move on. And we're going to start doing some calculations of lines. Just so you know, we're going to see some new notation here. This is some stuff that we are not familiar with yet. So first of all, this is the type of thing that you're going to end up seeing in geometry. All this means is there are 2 points, A and B, on a graph. And the line that goes between those 2 points on the graph, point A and point B, are formed by those 2 coordinates there. All it's saying is we want to know the slope of the line between those 2 points, and we want to know the slope of the line between those 2 points. That's all you need to know right now. I'm not going to get into the notation of geometry or anything like that because that takes time to teach, and that's not something that we need to learn. But the only thing you need to know is find the slope between these 2 points and find the slope between these 2 points. So we're just going to say, we're going to start off with AB right here, AB. And then the slope, we always use M. So the slope between those two right there. Now, we also need to use what? When you have 2 points on a graph and you're trying to find the slope, what do we use? You have 2 points on a graph and you're trying to figure out the slope. What is it that we have to use? I actually rewrote this on Friday of last week in that reference page that we did as notes. I'm going to go straight to that, and I'm going to go to the very last problem down here at the bottom. If you are given 2 points and you have to find the slope of a line, here it is, right there and there on the bottom left. What is this right here? What do we call that? Yeah, it's 2 points and we're finding the slope, which is the slope formula. So we're going to use the slope formula for the rest of this first page right there. So once again, I'm going to write the slope formula down off to the side here because we have room for it. So use the slope formula. M equals y2 minus y1 over x2 minus x1. We are using the slope formula for the remainder of the problems on this page, and I believe the first 4 problems on the next page. And we're gonna do 5 of these. We're not gonna do all 8 of them. We're only gonna do 5 of them. So starting with number 1, we've got our slope using these 2 points, -2, 3 and 2, 6, which means we've got an x1, we've got a y1, we've got an x2, and we've got a y2. I'm going to label these pretty much every single time. Now we're going to plug these into the slope formula, starting with the y2 value of 6. So 6 minus y1 is 3. That's the numerator there, 6 minus 3. The denominator, 2 is x2 minus -2 is x1. Whenever you subtract a negative, that is the same as adding. So I'm going to say 2 plus 2 on the denominator. So 6 minus 3 equals 3 on the numerator. 2 plus 2 equals 4 on the denominator. So the slope of the top line is 3/4. Now we need to figure out the slope of that second line. And it's CD, that's what we're calling that line. We need to know the slope of that line. So here's M. And then the slope, we got x1, we've got y1, we have x2, and we have y2. So we have our coordinates once again. We're going to do the exact same thing that we did to figure out the slope of this first one up here. So we're going to say y2, 3, minus y1, 0, over x2, 3, minus x1, -1. 3 minus -1, which would be 3 plus 1. On the numerator, 3 minus 0 equals 3. On the denominator, 3 plus 1 equals 4. So the slope of the first line is 3/4. The slope of the second line is 3/4. How can we identify these two lines? Can we identify them as parallel, perpendicular, or neither one of those? What are we going to say? You're going with parallel. Why is that? Do they have the same slope? Yeah, so the slopes are the same number, so the slopes are the same. And what do we know about parallel lines? Parallel lines have the same slope. Exactly. So I definitely agree with your assessment there. that because the slopes are the same, 3/4, 3/4, those lines have to be parallel. And that's the only thing we need to know about lines in order to determine if they are parallel or perpendicular, or perhaps neither one of those things. It's just the slope. It's all about the slope. So if you know the slope of two lines, you can know without even looking at them if they're parallel, perpendicular, or neither one. Ash. The initials? Yeah, so here's what you can do. With parallel, let's go back up here. There are symbols we can use for this. Parallel is like two lines kind of slanted diagonally right next to each other. So that symbol right there, that's parallel. Oh, that's fine. As long as they appear to be parallel, there's a symbol that we use for it, and it's like perpendicular is an upside down capital T. That right there. It's an upside down capital T, basically, right there. So if you want to use this symbol up here for parallel, you're welcome to use that instead of writing the word. If you want to use this symbol here for perpendicular, you can use that instead of writing the word. So 100%. So we can do that. Right down here for parallel. So we can say parallel, or we can use the word parallel, either way. So thank you for bringing that up. By the way, those symbols there, those are geometry symbols. So you've learned a couple things about next year's work already. By the way, you'll do this lesson again next year, just as a heads up. So you'll be prepared for it. All right. Number 2, let's look at that one. Let's figure out the slope of AB. So AB, yeah, take a pass. So we got AB, our slope. Here we go, x1, y1, x2, y2. So we're starting with y2 on the top, 4, minus y1, 2, over x2, 5, minus x1, 0. From there, we're going to just say equals 4 minus 2 is 2, 5 minus 0 is 5. So our slope of AB is 2 over 5, or 2/5. That's the slope of our first line right there. And then for CD, we've got x1, and y1, and x2, and y2. For the numerator, it's going to be y2 minus y1. So that's going to be 3 minus 8. So 3 minus 8 on the top, and on the bottom, the denominator, 3 minus 1, x2 minus x1. 3 minus 8 equals negative 5. And on the bottom, 3 minus 1 is 2. So our first line there has a slope of 2/5. And our second line has a slope of negative 5 over 2. So can we describe these lines as parallel, perpendicular, or neither based on those numbers? Ash? Yes, they are exactly perpendicular because remember, perpendicular lines have opposite reciprocal slopes or opposite signs and reciprocals, meaning just ask yourself this question. Is one of these positive and one of them negative? If the answer is yes, then you keep going with the second question, and that is, are they reciprocals of each other as well? Are they flipped over versions of the same fraction? If that is also yes, then that means they're perpendicular. So you got a positive, you got a negative, and they are reciprocals, which means that they are perpendicular. And we can just use the perpendicular sign and say perpendicular. All right. Are there any questions so far? Mathematically, we haven't done anything new right now. We're only using the slope formula. The new thing is just identifying, can you determine if a number is the same as another number, which you all can. And then can you see if something is an opposite reciprocal, which isn't quite as simple as identifying the exact same number, but it's something that you'll be able to pick up on pretty quickly. Ash. Let's look at number 3 and we'll find out. That's a great question. What happens if What happens if they're not the same number? What happens if they're not opposite reciprocals? Let's look at problem number 3. What's that? Yeah, so that's a really good question. I'll tell you that as well. But let's look at number 3, and then I'll go back and answer your question about number 2. So for number 3, our slope m is going to be y2 6 minus y1 8 over x2 2 minus x1 of -1. So 2 minus -1 would be 2 plus 1 for the denominator. So 6 minus 8 over 2 plus 1. 6 minus 8 is -2. 2 plus 1 is 3. So that is a slope of -2/3 for that first line. For CD, I know I'm moving a little bit quicker now, but I think it's time to speed up a little bit. We've used this formula a lot of times. On the numerator, 3 minus 2 over 3 minus -1, which is 3 plus 1. 3 minus 2 is 1. 3 plus 1 is 4. All right. Now, Ash, I know this doesn't exactly answer the question that you had for number 2. But what should we say about these? How do those two slopes relate in terms of the kinds of lines that we have? Would these be parallel lines? Are those slopes the same? No. We do have a positive and a negative, but are they reciprocals? No. So what should we say? Given our options up here, parallel, perpendicular, neither, what would be our answer? Yeah, neither. These are just two random lines. Oh, this will be neither. Yeah, it's not exactly the same, so they're not parallel, and they are not opposite reciprocals, which means they are not perpendicular. So these are neither parallel nor perpendicular. It's just two random lines with two different slopes. Now, going back, Ash, to your question about number 2, I'm going to ask you some further questions about that. Are you asking, like, if one of them was just like 2/5 and the other one was 5/2 without the negative? -4/2? That would become a neither, exactly. So what Ash was asking is, if this one stays a 2/5, and this one, instead of a -5/2, is a -4/2, that would turn into a neither because they're not reciprocals at that point. One's positive and one's negative, but they're not reciprocals. Also, I do want to mention as well, you don't need to write this down, but it will be kind of an important thing to take a look at. If you have, for example, let's say 2/5 and 5/2. This is also going to be neither. And this is where it gets a little bit more challenging, because a lot of people will say perpendicular for this, but in order for it to be perpendicular, one has to be positive and one has to be negative. These are both positive and they are only reciprocal. So if it's one or the other and not both, opposite and reciprocal, then the answer is neither. Same thing is true if you have 2/5 and -2/5. Again, this is neither. These are just opposites. They are not also reciprocals. It has to be both at the same time, opposite and reciprocal, to be perpendicular. So I just want to make that really, really clear before we move on. So, because sometimes you will see things like this and you'll have to make that determination if it's opposite, positive and negative, perpendicular, reciprocals, if it's a parallel, perpendicular, and neither. So, you know what? We're just going to do one more of these. Let's skip on to number 7. So go to the second page, look at number 7. All right. So number 7, we got AB. And AB says the slope M is equal to, all right, we got -4 minus 1 on the numerator. So -4 minus 1 on the numerator, and then 3 minus 3 on the denominator. So negative 4 minus 1 is negative 5. 3 minus 3 is 0. So that's negative 5 over 0. For CD, slope formula again, y2 minus y1, the top would be 5 minus 1. And the denominator, negative 4 minus negative 4 would be negative 4 plus 4. 5 minus 1 is 4. Negative 4 plus 4 is 0. Now, your first reaction probably is and probably should be neither. However, because they're not the same, are they? In terms of what we're looking at here, those numbers are not identical. But we just mentioned this a few minutes ago when we were looking at opposite reciprocal stuff, and I plugged into the calculator and there's a denominator of 0. What happens? If your denominator is 0, what does that mean about the slope? This is what Elena said. What did you say a few minutes ago about a denominator of 0, Elena? Undefined. Yeah. If your denominator is 0, then the slope is undefined. And if your denominator is 0, then the slope is undefined. Now what do we have? If they're both undefined slopes, that means the slopes are the same. So what does that mean in terms of the lines? If the slopes are the same, what kind of lines do we have? Parallel, yes. These are parallel lines. Nice. That's because these are both vertical. Undefined slopes are vertical lines. Both lines are vertical, meaning they're parallel. Yeah. And if they're both, if it's flipped around and both of the top numbers are 0, that means they're both horizontal lines, which means they're still be parallel. So yeah, actually, that's a good way of thinking about it. If there is a 0 in each of your slopes, it depends. If there is a 0 in each of your slopes, depending on if it's on the bottom or the top, you will either have parallel or perpendicular lines, no matter what. It's not going to be neither. If there's a 0 in each one of your slopes, it's not going to be neither. If they're both on the top or they're both on the bottom, then they're parallel. But if it's one of each, then they're perpendicular. Okay. All right. We got a few more to look at down here. And this is given equations. So here's the deal with these. All you need to know about these lines is what? I've mentioned this a few times already. The only thing that matters for parallel perpendicular is what? In terms of what we need to know about the line. It's the first word in the title of today's notes. What is it? The only thing we need to know about today are slopes. That's it. The only thing that matters are the slopes. So as we look at these equations, we only need to know the slopes. That's it. It's the only number we're interested in. Everything else is useful in other contexts, but in terms of determining parallel, perpendicular, or neither, the only thing we need to know about is the slope. Other than that, we can ignore the rest of it. So problem number 9, what's the slope of the first line? Y equals 7x plus 2. What's the slope of that line right there? 7. Yeah, so m equals 7. What about the second line? What's the slope of that one? 7. Yeah, m equals 7, m equals 7. Remember, in slope intercept form, the slope is the number next to x. So 7, 7. Are those parallel, perpendicular, or neither? On number 9, what do we say about those lines? Yeah, 100% parallel. Those are the exact same number. Parallel lines have the same slope. What's that? 90% parallel? Nope, they're either parallel or they're not. It's a very like, it's like a light switch. It's either on or off. It can't really be kind of functioning. So yeah, it either is or isn't, because if they're not, then eventually they will intersect. And in order to be parallel, they can't intersect. Now, Ash, I'm going to tell you though, if you're not necessarily dealing with lines on a flat surface, then there are different answers to that question that you just asked about, like 90% parallel, things like that. That can exist if the math isn't being done on a flat surface. So, but it does not apply to what we're doing here. Yeah. Like, actually, I know we don't have a lot of time left, but if you're doing math on a sphere, you can have parallel lines that do intersect. You've all seen a globe, right? Yeah. You know the lines of longitude on the globe? You know the ones that go north to south that are parallel, right? Okay. Well, the lines of longitude on a globe go parallel north to south, and they run right next to each other all the way down, but then at the poles, they intersect with each other. Kind of crazy. So depending on where you're doing your math, the type of surface you're using, these rules can change drastically. So, but for what we are doing, there's one definition of parallel line, and that is they do not intersect. So number 10, slope of the first one, what is it? What number is next to X on number 10? It appears to be perpendicular because we got a 4/5 slope on the first line, and we've got a -5/4 on the second one. Positive slope, negative slope, reciprocals as well, opposite reciprocal slopes. Those are perpendicular. Nice. Number 11. Ooh, let's look at that one. So this is what I was just mentioning a few minutes ago. So take a look. So just a minute ago, I said, if you have something like 2/5 and -2/5, this doesn't work for parallel or perpendicular. Look at our slopes here on number 11. What's the slope of the first line on number 11? Right here, what's the slope? -1/3. What's the slope of the second one? +1/3. Now I just said a moment ago that if it's something like this, it's not going to work for parallel or perpendicular. So we have to say neither for this one. Now these are opposites. This one's positive over here, this one's negative over here, but they are not reciprocals. They're not flipped over versions at the same time. And so you will see cases like that where it'll look close to either parallel or perpendicular, but it can't be either one of them because it doesn't work with either one, even though it's close. So going back to Ash's question a moment ago, with what we're doing, there is no such thing as 90% parallel or perpendicular. It either is or it isn't. Okay. The last type of problem that you're going to see is something like number 12. On number 12, do we know what the slope is on either one of those lines yet? Why not? Because they're what? They're not arranged to show us the slope. Exactly. The equations need to be arranged in such a way that what variable is all by itself for us to know what the slope is. Yeah, and what variable, what letter do we have to get by itself to know the slope? Yes, so get y by itself. Solve for y on each one of these. So this first one is in standard form. So here we go, a little bit of algebra to do. Hopefully this looks familiar because we did this on Friday during our review. We have to get y by itself, which means that there's a little bit of algebra. So we need to subtract our 1x from both sides. And that will be 6y equals -1x plus 30. And I know it's going to be a little bit tight to do the work on the other side. And then we have to divide everything by the number with y. This is converting from standard form into slope intercept. We practiced this on Friday. And so we divide everything by 6, and that'll be y equals negative 1 over 6x plus 5. The only number here that we are interested in, though, is this number right here, negative 1 over 6. That's our slope for that line right there. So m equals negative 1 over 6. Now this other line, this one right here, it's not in slope intercept form, but it's also not in standard form right now either. It's like kind of in between both of those, which actually makes our lives a little bit easier for this problem over here because the x is already over here on the second equation. All we have to do is get rid of the 3. So we just have to divide everything by 3, and then we're good to go. So divide by 3 all the way across. And that will be y equals 18 divided by 3 is 6. So that would be 6 over 1x. And then negative 6 divided by 3 would be minus 2. Our slope of that line there is the number next to x. That's the 6 over 1. So m equals 6 over 1. So here are the two slopes. Negative 1 over 6, positive 6 over 1. So what do we say? Parallel, perpendicular, or neither for this one? I agree, they are perpendicular. We have a negative here, we have a positive here. So one's negative, one's positive, that's what we want. And they are reciprocals. They're flipped over versions of the same fraction. So they're negative, they're reciprocals. So perpendicular will be our answer for number 12. We're going to do one more. We're going to go down to number 16, and that'll be our last one. And then I'll get you your assignment. So number 16. We have an x, and we have a y equals 6. We have an x equals negative 1. If you have a y equals just a number, this is what we did a couple weeks ago. This is a horizontal line right here. So horizontal. If you have just an x equals a number, that's a vertical line. How are horizontal and vertical lines related on a graph? What do they look like on a graph? Horizontal and vertical. Yeah. So what's the answer? Perpendicular, exactly. So if you have just an x equals and just a y equals, that's going to be perpendicular. If you have two of these, two y equals just numbers, then they're parallel. If you have two just x equals numbers, those are also parallel, but if it's one of each, that's perpendicular. All right, so that is it for today's notes. And if we need